In this presentation, I'll be discussing correlation length lower bounds for the random field Ising and Potts models. To begin with a presentation overview, I'll be summarizing the methods from a paper first available in 2020 due to Professor John Ding and Dr. Matteo Wirth, which is given by the numbering archive 2011.08768. And in this paper, amongst several things, they introduced the random field Ising model. And to provide some background on this model, I'll be providing and discussing the probability measure and expectation, in addition to the spontaneous magnetization. And from the spontaneous magnetization, we can begin to gain currency and discuss notions relating to the correlation length. And from some predictions that were raised by Imre and Ma relating to the Imre-Ma phenomena that was described in a 1975 paper, I'll be providing some main results which will with help from the greedy lattice animal. But besides the random field Ising model, it's also of interest to determine whether the arguments and notions that we'll be establishing will also be of use for other models. In particular, the authors suggest that the random field Potts model could also be of interest, which is another model in statistical mechanics, which I will introduce and provide a similarly oriented result with regards to the correlation length scaling. And just to be completely clear, this is the paper that I had mentioned from the archive that the work in this presentation is based off of, in which John Ding and Matteo Wirth provide a correlation length of the two-dimensional random field Ising model from the greedy lattice animal. The greedy lattice animal is an object and a related result that was made use by Telegrand in his 2014 paper that we will describe further in length. So first, we can begin by defining the probability and measure and expectation of the random field Ising model. As in many models in statistical mechanics, we first look to the Hamiltonian, which we will incorporate in our definition of the probability measure. And the random field Ising model is very much related to the classical Ising model itself, in that the classical Ising model is given by the Hamiltonian that's given on the first line of the slide, in which we can enforce plus and minus boundary conditions, and this Hamiltonian is a function of the spin sigma, in addition to the finite volume lambda of n, where n is some strictly positive integer. And this is given by a contribution of a minus of these two summation terms. One of the summation terms over from sigma u and sigma v is from the sites that are given within the interior of the finite volume, whereas the other summation, which is given by a plus and minus sigma u term, is responsible for vertices of the graph in spins that are located on the boundary. And from the Hamiltonian that's given for the Ising model, we can define the Hamiltonian for the random field Ising model by introducing the following modification. We can make use of the same Hamiltonian that's given for the Ising model, with the only difference is that we append another term to our Hamiltonian, which represents contributions of an external random field. In this case, this external random field, in the term given from the external random field, the h of v terms are given by standard normal Gaussian random variables with mean 0 and variance 1. And in addition to this disorder that we introduce into the Hamiltonian from these Gaussian random variables, we also have an epsilon parameter and a sigma u parameter. So far, what we have defined towards obtaining the probability measure is introducing the Hamiltonian for the Ising model and demonstrating how one can obtain the random field Ising model Hamiltonian from the classical Hamiltonian for the regular Ising model. And to define the probability measure for the random field Ising model, we'll have to make use of the following ingredients. For ingredient 1, we will want to sample some spin configuration, which is given by sigma. And for ingredient 2 in our probability measure, we will want to incorporate the inverse temperature beta, which is greater than or equal to 0. And for ingredient 3, we will need to make use of a partition function, which throughout the field of statistical mechanics and probability is denoted with a z, which we use to normalize the quantity that we're going to obtain so that it's a probability measure. And from ingredient 4, we'll make use of the Hamiltonian that was introduced in the previous slide. And with these 4 ingredients, we can obtain a probability measure mu for the random field Ising model under plus and minus boundary conditions, which, as we have been mentioning, is a function of the inverse temperature beta, the finite volume over which we will want to sample our spin configuration sigma, in addition to the disorder epsilon h that we introduce from a new term in the random field Ising model Hamiltonian. And it's given by the reciprocal of the partition function times the exponential of minus beta times the Hamiltonian. Besides the Hamiltonian and the probability measure and the expectation for the random field Ising model that we can obtain, we can also define the spontaneous magnetization. The spontaneous magnetization is a quantity that is of interest for many models in statistical mechanics because it allows us to determine to further study any related properties of the correlation length, which we will introduce in the next slide. In this case, the spontaneous magnetization is given by little m, which again is a function of the inverse temperature beta, the finite volume, and the disorder parameter, or the multiplicative factor epsilon to the disorder, which is given in the random field Ising model Hamiltonian. And we need to look at how we will want to study the spontaneous magnetization. We have to make use of the following quantity. For one, we need to take an expectation value with respect to the disorder of the external field, which is given by the boldface E. And within this expectation with respect to the external field, we have the expectation value of the spin located at the origin under plus boundary conditions with respect to the probability measure for the random field Ising model, subtracted from the expectation value of sigma minus 0 with respect to the probability measure of the random field Ising model Hamiltonian taken under minus boundary conditions. So the spontaneous magnetization, by and large, allows us to relate with respect to the expectation of the disorder of the external field, the difference of these two spins under one probability measure that's given in plus boundary conditions, which is in the first term, sigma 0 plus, in addition to the probability measure or the expected value of the sigma minus 0 term with respect to the probability measure of the random field Ising model under minus boundary conditions. And from the spontaneous magnetization, we can define the correlation length. The correlation length is given by psi, beta, m, and epsilon. So it's still a function of many of the parameters that we have been introducing for quantities in previous slides, and is given by a minimum of n. And just to briefly recall, n is the parameter that we introduce in the model for the size of the finite volume over which we would like to sample our random field Ising model configuration. And it's a minimum over n for which the spontaneous magnetization is less than some threshold little m, which can be a parameter which is strictly between 0 and 1. So from the correlation length, or we can define the correlation length from the spontaneous magnetization in this fashion from the random field Ising model probability measure. And related to the discussions that we've been having for the random field Ising model is the Imry-Ma phenomena. This was first roughly described in a 1975 paper provided by Imry and Ma, which is titled Random Field Instability of the Ordered State of Continuous Symmetry. And by and large, their focus and their predictions largely relate to the disorder term, the random disorder term, which we introduce in the Hamiltonian from the random field Ising model, in which they state for epsilon sufficiently small, where epsilon is the multiplicative factor that is given in the random field Ising Hamiltonian, that depending upon the dimension, long-range order can either persist in 3 dimensions at low temperature, or no long-range order can exist in 2 dimensions. So this phenomena is related to what we have been talking about with respect to the correlation length, because it's going to relate to the definition of the greedy lattice animal, which is another quantity, which will allow us to quantify the ratio between the contributions from the random field with respect to the boundary of the finite volume. And besides the results that we've been also discussing so far, we can actually precisely quantify the main result from Professor John Ding and Dr. Matteo Wirth, in which they provide upper and lower bounds on the correlation length for the random field Ising model. And is given by this theorem 1.1 that they state, in which for a choice of the spontaneous magnetization strictly between 0 and 1, as we mentioned previously, there exists some constant which is dependent on the spontaneous magnetization that is also strictly positive, for which the correlation length of the random field Ising model can be bound above by some exponential, where the power of the exponential is dependent upon some epsilon to the minus 4/3 power for all positive inverse temperatures, including infinite inverse temperatures. And on the other hand, they can provide also a lower bound for the correlation length of the random field Ising model, in which the correlation length at infinite beta, which is still a function of the spontaneous magnetization in epsilon, is bounded below by another exponential, which also has a power that is dependent on epsilon to the minus 4/3. So we mentioned these results to give an idea or to give some intuition regarding the argument of the authors and how it relates to the Imry-Ma phenomena and other motivations and characteristics of the random field Ising model that we have been introducing. But besides the previous result, the greedy lattice animal also comes into play. This is a quantity that was introduced in 2014 by Talleyrand, and he made use of this quantity in an inequality that I'll demonstrate in the following slide. And he defines it as the following ratio S of n. First of all, we want to take the maximum over some script A of n term, where A of n is defined to be the collection of all collected subsets of lambda of n that contain the origin. And the greedy lattice animal itself, besides this maximum over A of n, is given by a ratio in which in the bottom part, downstairs in the ratio, we see the cardinality of the boundary of A. In addition to, on the top upstairs in the ratio, we have the summation of the Gaussian disorder over all sites V contained within A. And the greedy lattice animal will come into play in the arguments because an upper bound on the greedy lattice animal readily implies a lower bound on the correlation length for the random field Ising model. And it will also be shown that this argument can also apply to the random field Potts model, which is another model of interest. And so the upper and lower bounds on the greedy lattice animal, as we had just been mentioning, respectively imply lower and upper bounds on the correlation length. And this is given by the following inequality, in which from another result due to Professor John Ding and Dr. Matteo Wirth, we see that they can obtain an upper and lower bound for the greedy lattice animal, which is very reminiscent of the powers of the exponential that are raised in the correlation length that was given in a previous result. In the lower bound for the greedy lattice animal, we have contributions from a log n raised to a 3/4 power, which is multiplied by the reciprocal of some strictly positive constant c, whereas in the upper bound for the greedy lattice animal, the upper bound is very similar to the lower bound, with the only exception that we have a c instead of the reciprocal of c, in addition to the log n of the 3/4 factor. And the 3/4 exponent in the correlation length scaling arises from a 2014 proposition due to Talleyrand. And this proposition is given by the following result that's given below. He basically defines the collection of simply collected lattice animals that are contained within some finite volume with script B sub n. And then he looks to see how he can upper bound the following probability. He asserts that there exists a strictly positive constant such that for n greater than 1, we have that the following inequality holds, we can look at the probability where this p term is given by the probability with respect to the disorder that we introduce, the Gaussian disorder, and the maximum of the greedy lattice animal, the probability that the maximum of the greedy lattice animal exceeds C of 1 times some 3/4 factor from log of n plus u is bounded above by an exponential n minus u squared over 2. So from this proposition, we can make use of the result from Talleyrand, which not only allows for the authors of the paper that we have been discussing to obtain a correlation length lower bound for the random field Ising model from a upper bound on the greedy lattice animal, but can also be applied to the random field Potts model as well. And so, briefly to summarize, as a result of the 2014 proposition, as we have been discussing, from theorem 1.6, we can look to obtain an upper bound on the greedy lattice animal, which takes the following form. We can upper bound the expectation with respect to the Gaussian disorder of the greedy lattice animal, which admits the upper bound c a log n to the 3/4. And from this upper bound that's given in theorem 1.6, we can readily obtain, as demonstrated from Ding and Worth's arguments, the lower bound for the correlation length of the random field Ising model that's given in theorem 1.1 from the lower bound, which is characterized by the fact that there's an exponential with some epsilon to the minus 4/3 scaling, as we have been previously mentioned. But besides these arguments that we've been mentioning, one can wonder whether the 2014 proposition due to Talleyrand can also be applied to for lower bounding the correlation length of other models, in particular the random field Potts models. The authors suggest that the random field Potts model would have a correlation length scaling that agrees with the correlation length scaling that they established for the random field Ising model. And very briefly, to describe how the arguments would carry out in the main techniques, we can begin by defining the random field Potts model and introducing the related quantities to see how the argument would go. So first of all, we have to think to make use of a Hamiltonian. From the Hamiltonian that's given for the random field Potts model, we can take either wired or free boundary conditions. And this Hamiltonian is a generalization of the Hamiltonian for the Ising model and for the random field Ising model alike, because it is a function of the spins S in addition to the finite volume lambda of n and the number of colors Q in the external field H, which plays the role of the Gaussian disorder that was originally introduced for the random field Ising model Hamiltonian. And this Hamiltonian is similarly given by the fact that it can be defined with a minus beta times a contribution from two terms. We can either have contribution from terms that are given in the interior of the finite volume, which is given by a Kronecker delta of S sub I of S sub j, which determines whether Si and S sub j are equal from any possible Q values that the spins of the random field Potts model can take, in addition to another term which encapsulates the disorder from the random disorder from the Gaussian field, which is given by epsilon H sub I of alpha term times another Kronecker delta. And the difference between this term that we append to the Hamiltonian, which plays the role of the Gaussian disorder that was originally introduced for the random field Ising model, is given by the fact that there's an additional summation that's taken over alpha, from alpha being starting from 0 to 1 minus Q. And from the random field Potts model Hamiltonian, a corresponding probability measure can be defined. Under the same classes of boundary conditions that we introduced in the previous slide, we can look at the probability measure, which is a function of beta, lambda of n, and h, in the probability of sampling some Potts configuration S, some random field Potts configuration S, is equal to the reciprocal of the partition function times the exponential of the minus inverse temperature of the Hamiltonian, which is very much of the same form that was given for the probability measure for the random field Ising model. And besides defining the probability measure and how we incorporate the Hamiltonian into the probability measure, we can look to define the greedy lattice animal for the random field Potts model. So the greedy lattice animal, it takes a very similar form for the random field Potts model as it does for the random field Ising model. What the only difference is that we look at a very similarly defined ratio, with the difference that the numerator that we give in the ratio is instead given as a summation over alpha from 0 to 1 minus q, which is consistent with the fact that that the spins that are given in the Potts model can take on q values instead of either plus and minus that was given from boundary conditions that we use to define the random field Ising model Hamiltonian. And this quantity script g sub n corresponds to the greedy lattice animal, and we take the maximum of this greedy lattice animal, which is given by the ratio of the contributions from the Gaussian disorder with respect to the cardinality of the boundary of A, which is given by the same collection of simply connected subsets of lambda of n, namely that these subsets contain the origin, so that they have non-empty intersection with the origin. And as we had alluded to previously, Talleyrand's 2014 result applies in the following fashion. The proposition that he provides us with that is stated for the random field Ising model directly applies and carries over to the random field Potts model, with the only difference is that we take the probability measure, which is given by script P, which is given by the Gaussian disorder that we introduce in the Hamiltonian for the random field Potts model. In the upper bound, in addition to the components that we look within the probability, are the same. Namely, we have an upper bound of exponential to the minus u squared over 2, which we had already established and briefly characterized for the upper bound in the proposition that was applied in the case of the random field Ising model, in addition to the fact that there is still a log n to the 3/4 factor plus u, which establishes that from the proposition due to Talleyrand, there is the correlation lane scaling for the random field Potts model coincides with the correlation lane scaling for the random field Ising model. And we take this collection, the maximum that we use to define the greedy lattice animal that appears in this proposition, which is an adaptation of Talleyrand's result, is given by the collection of simply connected greedy lattice animals, which is script B sub n. And so, from an upper bound on the greedy lattice animal for the random field Potts model, a correlation length lower bound is obtained. And this is given in the adaptation of Professor John Ding and Dr. Matteo Wirth's results in Theorem 2, in which we can obtain an upper bound to the expectation with respect, where this expectation is denoted with respect to the random field that we introduce, or the Gaussian disorder that we introduce in the random field Potts model Hamiltonian, which is similarly upper bounded by some c times a logarithm in n raised to 3/4 value for all n greater than or equal to 3. And to conclude our presentation, I wanted to provide a presentation summary and conclusions. So what we began this presentation with was we first introduced the random field Ising model and some related quantities which we can further characterize relating to some predictions from Emery and Ma in their 1975 paper, which were later rigorously characterized by Eisenman and others. And from our description of this correlation length scaling, we can establish connections with the random field Potts model and establish that this model, despite having some difference in how we introduce and incorporate Gaussian disorder in the Hamiltonian for the random field Potts model versus in the Hamiltonian for the random field Ising model, actually ends up not mattering and not being material because we can still obtain the same correlation length scaling. And in doing this, we provided adaptations of results due to Ding and Wirth, which were adapted from a proposition due to Talleyrand. And thank you very much for your attention.